So I'm very happy to introduce you to Professor August Gudmundsson, who is giving our outreach talk today, titled Energy Transitions Through Geothermal Energy and Other Renewable Sources. Over to you, August.
Well, thank you, Jürgen. So, yeah, I'm going to talk about energy transition through mainly geothermal energy, but I will mention other renewable sources as well and have a look at it here. So what is energy transition? Energy transition means that we are shifting from the use of fossil-based energy production and use, including, of course, oil and natural gas and coal, to renewable energy sources. And here we have an overview of the main renewable energy sources. We have wind energy, can be onshore and offshore. We have marine energy, which in the UK would be, for example, in the Bristol Channel. We have solar energy. There are several types, that is PVs, these ones here. There is solar heating and then concentrated solar power. We have hydro energy, where you need the dams. And then we have geothermal energy, which will be the main focus here. And we have shallow geothermal energy. And we have deep geothermal energy. And we have deep, both natural deep and human-made deep geothermal energy. Then we have bioenergy. I will not really discuss that much. This is of course, the oldest one of these renewable energy sources. Why is the shift taking place now? Well, partly at least, one of the main reasons is that the surface of the Earth is becoming warmer. And people are worried about it becomes too warm, too hot. So what is the heating? If you go back in time to measurements in the 19th century, that was, of course, a very cold period. We see that there is in a 5-year mean average variation here, the brown one, it's around 0.4, 0.8 degrees now, above the baseline of 14 degrees. So this is causing people to worry and is one of the main reasons we would like to go to renewables. Another reason that is not mentioned so often is, of course, pollution. Pollution in general has effects on health and is in highly populated countries like UK is a serious issue, or can be. So what could possibly happen if we allow things to go on? If it's 2 degrees, this is one idea, what it could look like in the future if the temperature would rise by 2 degrees Celsius and we did do nothing. Of course, we would definitely do something before our parliament would be in this situation here, but this is an indication of how it could possibly be. Renewable energy sources are plenty. They're absolutely plenty. In fact, it's easy to show that the renewable energy sources can provide 3,000 times the current global energy use. And most of that energy would come from the sun. The sun is by far the greatest source of renewable energy. Here are the sources, the main renewable sources. But they can be divided into two main classes. One, unsteady source. The other one, steady. What do I mean by that? Steady source is one that is always there, day and night, winter and summer. And geothermal energy is, of course, one that comes to mind, number 4. Unsteady sources like wind energy and solar energy, and in a way marine energy, part of it at least, is not always there. For example, when there's night, there is no solar energy, and when there is a cold, still winter night, there is no wind energy either. And therefore, it's so important when we are going in this direction is to combine steady energy with unsteady ones. So if you have solar and wind, which we're already doing here in the UK and Europe and many countries, to combine it with geothermal energy is an ideal situation, because then we combine the steady one that is always there with the unsteady that sometimes gives us a lot of energy, and in some days little or hardly any energy. So I'm going to focus mainly on the geothermal energy. It's closest to Earth sciences, and of course a field I've worked on for many years. But I've also worked on, in later years, on solar energy quite much. So I would like to show you some comparison with Britain or the British Isles with the rest of Europe. So people often think that the sun is not shining very much in Britain, but in fact in southern England, it is not too bad. Solar energy is in fact not too bad there. Of course, we have plenty of wind energy in UK. These are windy islands, and people therefore often think that because of the wind and rain and so on, the solar energy is not so great. But it is similar to central part of Europe, like parts of Germany, which is one of the leading nations in the use of solar energy. We see it maybe better here. So this part of England, particularly this southern and southwestern and southeastern parts, these are all reasonable. These are reasonable areas, and if you drive around there, you see people are building or setting up solar farms already, particularly in this area here, southeastern England. But we see them also down in Cornwall and so on. And because we have high wind speed, that helps to cool the panels, if you're talking about solar panels. And in addition to producing electricity itself, it is helpful in cooling the panels. So let's move on. So now we go to the main part of the talk, which is geothermal energy. There are three main types: deep natural geothermal energy, deep human-made energy, and shallow energy. So let's go through these. First, where does the heat come from? It comes from inside the earth, of course, but when we're in active volcanic areas like here in Iceland, this is an erupting geyser in Iceland, and erupts every 5 to 10 minutes. So if you go to the country, to make a little bit propaganda here, if you go to the country, you will definitely see this one here if you go to southern Iceland. There is an older one called geyser or geyser. That one erupts very infrequently today. So if you look at active natural geothermal fields with high temperature, they are usually related to magmatism. So yes, there is a flow of heat out of the earth, and of course the outer core of the earth is molten, but the heat that we are talking about for these active geothermal fields in volcanic areas is mostly coming from magma. It comes from magma. And here we see example of that. This is from eruption in Iceland. It was a relatively large one in 2014 to 15, lasted nearly half a year. And the magma that comes up is 1,300 degrees. And when it solidifies at depth, this magma gives heat to geothermal fields. Of course, occasionally, even at the surface, it can give rise to geothermal fields, so it can be used for heating, as we see here. This is an eruption that happened in Iceland in 1973 and partly destroyed the town offshore South Iceland, fishing town, 5,000 people. They are told to be evacuated. But the thick lava flow that formed here is, for those who are interested in petrology, this is andesitic lava, so it's very thick, and it contained the heat for decades. So after this eruption stopped and they rebuilt the town, they used the lava here, the interior of the lava, to produce hot water for the town. So it was not all bad, in fact, in this situation here. So the heat sources in natural geothermal fields are like here, magma intrusion. This we would normally call a magma chamber, shallow magma chamber, a couple of kilometers or a few kilometers depth. It also sends out what we call dikes or inclined sheets. We see here they can produce heat for geothermal fields for decades, and then the hot water goes up partly through the porous, tiny fractured rocks, but also uses very much faults. And faults are generated in connection with earthquakes, and therefore we see often that geothermal fields become renewed when there's earthquake activity. We saw it beautifully in Iceland in the year 2000 when we had two big earthquakes in southern Iceland, in one of the main geothermal fields, and then this famous geyser or geyser started to erupt again, had been more or less dormant for decades. So earthquake activity renews the permeability, renews the paths for the hot fluid to go through up to the surface. So as I said, this is the same town I mentioned earlier from 73, and the geothermal gradient in Iceland is normally high. Even in the oldest part of Iceland, it's around 37 to 40 degrees per kilometer, but in the volcanic areas, it's 165. And in fact, where you have shallow magma chamber is much, much higher, because when you have a shallow magma chamber, the roof of the chamber can be at 1, 2, 3, 4, 5 kilometers depth. So as soon as the drill hole would go in there, and we have drilled into several magma chambers in Iceland by accident, basically, there the magma is maybe 1200, 1300, 1400 degrees. And now one of the main geothermal approaches in Iceland is to really drill into extremely hot rocks, hundreds of degrees, to increase the efficiency of the energy production. In UK, particularly in Cornwall, we have up to 40 degrees per kilometer, the gradient, so how quickly the temperature rises with depth, which is in fact quite good. And those are related to old magma chambers, long dead fossil magma chambers in the United Kingdom, but they're still hot. We call them plutons. They're granitic plutons, and they are still hot. And I will come to this in a moment to explain how we use it. So we have high temperature fields in Iceland, where the temperature is above 200 degrees at 1 kilometer depth. So these are usually related to volcanoes. These are red spots. Then we have low temperature fields where it's less than 150. They're usually in the older parts of the country, like you see here. Here is a typical high temperature field in Iceland, in northern Iceland, close to, in fact, a geothermal power plant called Krafla. And that was an unlucky start, because that power plant was being built and the drill holes were being made, and then a volcanic eruption started. And one of the dikes, the magma field fracture, went into one of the drill holes, and the eruption came up through the drill hole. So it was a difficult situation for 10 years, but now it's producing electricity and heat and so on. So we have mud pots and we have steam vents. These are steam vents. And here we have mud pots, not very appealing. If you go to the geothermal fields, these are very popular for tourists, just follow the paths, because the paths may change, because the field is changing all the time, and it's extremely unpleasant to put your foot into one of these. They're 100 degrees, of course, they're boiling. You can see the old geothermal fields in Iceland very well. This is close to Reykjavik, the capital of Iceland. In fact, the geothermal energy in Reykjavik is partly from this old volcano. It was active 2.8 million years ago, has been eroded by glaciers, so we can see into it. And these little strange inclined layers are intrusions, old magma-filled fractures. We call them inclined sheets. They're not vertical like dikes, they're inclined. And they produced heat. And we see the alteration here, this grayish, bluish areas. This is alteration here. So this is an old geothermal, high temperature geothermal field. But Reykjavik is still getting part of its geothermal waters, the low temperature ones, from this old volcano, from plutons related to this old volcano. So if we go to the oldest part of Iceland, we can see also the geothermal gradient there, as I said, maybe around 40 degrees per kilometer. But in addition, we have these dikes. So the inclined layers here are lava flows. These are thick dikes. And whenever you need to look for fluids in the Earth's crust, water particularly, you look for dikes, because dikes and faults conduct fluids. In fact, particular, if the fluid comes down here, it would often be arrested or stopped at this thick dike. These dikes are up to 10 meters thick here, and will be channeled up to the surface as a warm spring, So the low temperature fields in Iceland are very commonly associated with dikes or faults, so fractures. Now we go to the active area, and this one is called Hengill. It's a beautiful lake here, Thingvellir. This is inside the active volcanic rift zone in Iceland. And all these faults here are conduits for geothermal fluids. And then one of the main power plants is in fact here. I will show that power plant to you in a moment. These faults are active earthquake faults. Some of them are quite curved here, and they go into young lava flows here, and therefore the displacement, the movement is smaller there, and they conduct fluids, and we can often see the geothermal springs aligned along these kind of faults. So what I showed you now was this area here. So this is the lake I showed you. This is the two main power plants in Iceland. Hengill are in the volcano Hengill. They're called Nesjavellir and Hellisheiði, and Nesjavellir is located here and Hellisheiði located here. And these produce electricity and the warm water, the hot water for the capital area of Iceland, Reykjavik, which is here, located here. Iceland is here. Iceland is a little bit bigger than Ireland, around 100,000 square kilometers. In comparison, Britain is 243,000. So you have an idea of the size. So here's a 25-kilometer long pipe conducting hot water from this area here to the Reykjavik area for heating houses. And the volcano, the old one I showed you, the old geothermal field was here, and is also used to get hot water. By the way, there was an eruption here last year. This is a geothermal field here, and there are many geothermal fields in this area here. There was an eruption here last year, and then now this magma is accumulating again in some of these geothermal fields here. So we might have another eruption this year. Here is the one of the main geothermal power plants. This one is Nesjavellir, the one close to this big faults. These are the faults I was showing you on the aerial photograph, and this is the lake I mentioned, the shield volcano here, Table Mountain there. So this has been a great success story, producing both electricity. So remember, the heat is always higher than the electricity because heat is a very low quality energy. So it's very difficult to transform heat into mechanical or electric energy. But anyway, we get here similar to a small nuclear power plant. This one here is the total production in Iceland. You might say, well, that's not very much. But then you have to remember the total population in Iceland is only 370,000 people, similar to one of the medium cities in the UK. So this is plenty of energy for Icelanders. So what do we use the geothermal energy for? We use it for electricity, of course, for greenhouses to grow tomatoes and everything we really like here, and swimming pools. But in addition, we use it to heat the streets. Iceland is, as the name implies, is a rather cold country. And in the winter in Reykjavik, in the capital, we often have ice and snow on the streets. So the rest hot water coming out of the houses here, they're all heated by geothermal energy, can be put into these pipes under the asphalt and then used to melt ice and snow in the wintertime. This shows quickly how the geothermal energy use has increased in Iceland in the past decades, very rapidly after 1970. There was an energy crisis then in 74, very much increase here. Coal hardly used at all, and oil, of course, mainly for transportation. And hydropower is not likely to increase very much in coming years or decades, I think anywhere in the world, because it's unpopular from the point of view you have to put a lot of of land, even a huge valley or even a part of a city, underwater to make the dam. So it's not popular from an environmental point of view. But of course, it's a very clean energy. Hydropower is a very clean energy. Now I come to the deep human-made resources, and here we have those. We call them either enhanced geothermal systems, EGS, or hot dry rock, HDR. And the idea is beautifully simple. You find a pollutant, you find a granitic body, or body that is hot, say at 4 to 6 kilometers depth. You pump cold water. The cold water causes slight movement and tiny earthquakes, most of them not felt by humans, on fractures there that exist there, and increase the permeability, increase how easily the fluid can flow. And the fluid flows through the hot body and takes up the heat. When the temperature of the fluid is around 150 or even 200 degrees, you take it up to produce electricity and to heat houses. And it works. In the Rheingraben in Germany for decades, we have, in the Rhine, well, the part of it is in fact in France, where the power plant is. We have produced electricity for decades there by first pumping cold water in the center, let the water migrate through the hot body here and take it up. How do we know the size of the reservoir, the human-made reservoir? Well, we use micro earthquakes. Each point here is a little earthquake, so small that you wouldn't normally notice it, but they can be detected by seismometers. So when the cloud of earthquakes has become very big, we drill a new hole, say here, or maybe in this end here, and then the water has migrated from there to there and taken up the heat, and then we have the production well. So this idea is very simple. You pump cold water down here, you let it circulate or migrate through the hot body, and when the water is hot enough for electricity or for house heating, you take it up again. Here, for example, showing it's going up to 150 degrees. So in UK, in the oil crisis in the 70s, there were projects here, particularly in Cornwall, in the granite there. Then the whole activity was transferred to Jules in France. That's part. This Jules is a part of the Rheingraben. It's on the French side of the Rheingraben, where they've had a power plant operating for decades now. There is an additional one in Southampton and several others where you're not taking up hot enough water to make electricity, but you can use it to heat houses. Now there is a project in Redruth in Cornwall, United Downs project, and that looks to be very successful. And the idea is to begin by producing 10 megawatt electricity, which is not very big, but 60 megawatt of thermal power. And this will be used then for electricity production and for heating houses. It has been estimated that up to 20% of the UK's current annual electricity use could be possibly produced from such hot bodies. So here's an overview. Redruth is located down here in Cornwall. So we have these granitic bodies here in northern England and in Scotland. They can produce theoretically at least electricity. Then we have hot sedimentary basins where we can get hot water and for using it for heating of houses. This is the thermal heat flow in the UK. You see it's highest here in Cornwall, where the red spots are. So we have many possibilities for deep geothermal energy in the United Kingdom. So what do we have exactly? We have several sedimentary basins where we can get 60 degrees water and up to 77 in Southampton for heating houses. Then we have these granitic bodies, these pollutants as we call them, where theoretically we could reach maybe 200 degrees, so easily produce electricity. And the current project here is supposed to reach up to at least 190 degrees or something similar to that. Then the final one is on very shallow geothermal systems. Now, strictly speaking, the heat here is not, except in part, coming from inside the earth. It is really coming from the sun, because the heat is simply the temperature of the groundwater. And that temperature corresponds to the average yearly temperature at the surface as given by the sun. But the beauty here is we can use this shallow geothermy to heat the houses in the wintertime and cool them in the summertime. Yes, occasionally we have here 27, 30, 33 degrees in UK in the summers, and we need cooling. And we can use this temperature from the groundwater, from the soil and shallow ground to cool. So the main ideas are two. There's some use this kind of pond, but the main ideas are two. Either use a loop, we'll show you in a moment. That's particularly when you're building a new house or you have a big garden that you have not really planted trees and flowers and so on in. Or you drill, if you have an older house and an established garden, you drill in the corner, you drill a hole that can be 50, 100, up to 250 or even more meters deep. And there you have the heat exchange, and you use it to heat your house or cool your house, depending on the season. So, at several meters depth, as we all know, the temperature doesn't really change over the year. It stays more or less similar to the average temperature at the surface. That's, of course, where these animals are living, hedgehogs and badgers and whatever. They live in these areas where the temperature doesn't really change very much. Now, if you look at UK, the coolest part would be in northern Scotland, around 8 degrees average temperature. And here in the south, we have 12 to 30 degrees. So what do we do? Let's say we do it here where we are based now. We take the 12 degree heat into the house and we compress it. And when we compress it, it becomes warmer. As everyone knows, when they're pumping into a tire, it becomes warmer. And when it becomes warmer, we can make it as warm as we want. And we would normally take it up to the heat we like to have in our house, let's say 20, 21 degree. And that we use then to heat the house. We use an electric pump or electric instrument to do this, but it's still very efficient from an energy point of view. As I say, we can go to 250 in Switzerland, where I worked on this project. Occasionally they go more than that, but usually it's 250 or less. In the wintertime, we do not compress the hot air here. We keep it at 12, 13 degrees, and we use it. No, sorry, in the summertime. In summertime, we keep it at this temperature to cool, if necessary, the house. But of course, in wintertime, we compress it to heat it up to 21 or 22 degrees. So here's an example. This is a loop, very shallow one, maybe 2 meters depth in the ground. Obviously, there's plenty of space here for it. So this would be a loop that would then provide 12, 13 degree fluids or water into the house, and there we can raise the temperature as we please. Similarly here, they're working on it. These are all from southern England here, as you see here. The idea is this one here, and some people use ponds, but that is not very popular. So it's mainly the loops or the vertical drill holes. So you can use heat pumps everywhere. Even in cold countries like Sweden, they're very, very popular. They're enormously popular in Germany, and they're becoming more popular here in UK. Why should we go for that? Well, first of all, they're very versatile. They can be used for heating and cooling. Now, in urban areas, the general yearly temperature is 2 to 3 degrees warmer than around in the surrounding areas, suburbs. It's called heat island effect. And the cost is relatively low. And the government has long time ago planned to take out boilers in new houses after 2025. So we need an alternative. So this also helps to cut our cut our greenhouse gas emission by maybe 1/3. So what's the geothermal situation in the world today? Well, there are many countries here in green that are already using geothermal energy, a lot of them, and growing every year. This is the power, the electricity installed in the world today, and is increasing rapidly. United States is still on the top, but there are many other countries coming in. Turkey has come in lately, very strong. Philippines have been for a long time. Iceland is here, and this is increasing very much. So if you look at the forecast of the European Geothermal Energy Council for first as it is now, this is from 2020. Yes, of course, it's very great in Iceland in proportion to the others, and these are mostly natural geothermal energy sources. So EGS, Enhanced Geothermal Systems, or hot dry rocks, is planned to increase in the future to 18% of this. And that's the optimistic forecast for year 2050, where they forecast that up to 4,000 terawatt, 1 terawatt is 10 to the power of 12. They forecast that up to 4,000 terawatt could come from geothermal energy in Europe. And for comparison, the total energy consumption in the UK today is 1,650. So we are talking about several times the total energy use in the United Kingdom coming from geothermal energy in Europe in the future. Obviously, in active areas like Turkey and Iceland and part of the Central Europe would be most popular or most likely to be successful. So the ideal thing is to combine a steady source like geothermal energy with the unsteady ones. We know that solar and wind energy are increasing faster than any other renewables. They are increasing in a very similar rate every year now, have been for decades. So they're increasing enormously. But combining them with a steady source like geothermal should be an ideal situation. And to end on a little propaganda here for Holloway, so we would be very happy to see you come here and learn about renewable sources. We teach about all of them, not only geothermal. We teach about wind and solar and hydro and marine is also included. But the focus is, of course, on geothermal energy with then secondary on solar and wind energy as the main thing. And with those words, I think I say just thank you very much indeed.